All right, class. Welcome to the 5.1b lesson. It is on exponent properties. So we're going to continue our understanding, continue to learn about exponents. And um, let's first start with a pretty simple task. It says, what does 3 to the fourth times 3 to the sixth simplify to, right? Choose all that apply and explain your reasoning, okay? So I don't know what the answer is. Let's do this together and let's first remind ourselves some rules, right? So 3 to the fourth really is 3 times 3 times 3 times 3. Uh, Remember that the 4 represents how many times you need to ask the base to multiply itself, right? So this is 4 repeats of multiplication. 3 to the sixth would be 3 times 3 times 3 times 3 times 3 and times 3. So really, if I multiply 3 to the fourth times 3 to the sixth, how many total threes do I have in that product, right? Wouldn't you say, class, that that would actually be 3 to the 10th, right? So you can see that E is a correct choice. But are there any potential other choices? Is 3 to the 10th equal to anything else you see on the screen? Go ahead and decide what you think is correct. I'm going to go ahead and I'm going to use process of elimination to help me out. 9 to the 24th power. I know that's interesting, but that's a very, very large number, right? So there's no way that this could be true. Um, I can see why they did that. 3 times 3 is 9, 4 times 6 is 24, but no, that's not correct. But is 9 to the fifth correct? Let's just think. If I have 3 10s, right? I'm going to try to do that. 3 10s. Or 10 threes, I should say. A product of 10 threes. This is what it's going to look like, right? And notice how I kind of bunched them into pairs because I knew that that was going to create a really just a repeated multiplication of 9. And that actually is correct. 9 to the fifth power does work as well. Um, I don't know what 9 to the fifth power is. Obviously, I can calculate that, but I'm going to use my calculator to tell me what that is. And 9 to the fifth power is 59049. So, because that's true, I know that D also works, right? And then 6 to the 24th power, I'm a little weary of. I don't like that because anything raised to the 24th power is really, really big. And 6 is not really even that small of a number. So 6 to the 24th power, to me, doesn't sound right at all. And it is in the millions, right? So totally wrong. 6 to the 10th power, I know that kind of seems reasonable, but no, that is not correct either. Okay, so hopefully you got A, or you got B, D, and E. Explain how to multiply exponents with the same base without expanding. Use an example to justify your explanation. Okay, so I like to use a simple example of like x squared times x to the fifth, right? That simply is just x times x times x times x times x times x times x. I'm showing this, but really, I hope you realize that the shortcut is if they have the same base, right? This is only true if they're the same base. X is the case for this. What you simply do is you just add the exponents, right? So this is rule number one with exponent properties. The algebraic rule for let's see, the algebraic rule for the product of powers states that if you multiply x to the a times x to the b, you literally get x to the a plus b. Now, eventually, you will run into maybe potentially negatives, and that's a little bit of foreshadowing of what's to come. But so far, we're only dealing with positive integers. Eventually, later on in this module, we'll deal with negatives. Okay. So really, this is a good opportunity for you to just practice your skills. I really think 4 through 12, you should try on your own. So go ahead and just try to do this as I'm explaining it. I'm going to I'll run through these really, really fast. And then obviously you can compare your answers with this video. Okay. X to the 5th power times X to the 3rd is literally X to the 8th. X to the 40th with X to the 3rd is X to the 43. X to the 43rd power. Here, 6, we notice that we have two different terms now. We have a base of A with a base of B. So obviously, you combine like terms. You only compare, A3 times A6, and then B squared with a B3, right? So then when you simplify that, you end up getting A to the 9th and B to the 5th. Okay. Obviously, you can also do this without, much work because it's pretty simple so far. All right, so let's keep going. Number 7. Again, you should probably practice this on your own and then refer to the video. But xn times xn times x to the n. Remember that we are combining the powers because they all have the same base. And we are multiplying in this case. If we were dividing, it would be a totally different story. But this is x to the n plus n, right? Which ends up being x to the 3n. Okay, now something like number 8, you kind of want to first identify the like terms, like the like bases. The 8, the number is always before the variable, right? So I kind of already know that 8 is just by itself. There's nothing I need to multiply with 8. If there was another value in front of the AB5, I would actually multiply 8 with that number, right? Remember, at the end of the day, we are still multiplying things. So there's like a 3 here and an 8 there, it would be 24. Okay, so then A with A squared is A cubed. B5 with a B is B to the 6th. Not too bad. Okay, so let's box. Here, number 9, just like I said, there's a 2 now in front and there's a 4. I like to do those, calculate the product of that first. That's 8. X with X squared is X cubed. Y with Y to the 3rd is Y to the 4th. And then Z is all on its own. So there is nothing left to do with Z. I hope we're realizing that your variables do need to be in alphabetical order. Just like we've always been working with in the past, variables should always be placed in alphabetical order. Okay. Number 10, notice how my exponent is an expression, but that doesn't mean that we have to do anything different, right? We still have to add the exponents because the y's are the same base. So n plus 1 plus n minus 1 is actually going to give me just 2n. The 1 and the negative 1 cancels. Okay, here it's negative 1 with a negative 1, and that's like a negative times a negative, which means it's a positive, right? A with A squared is A cubed. B with B5 is B6. You can see that these questions go by pretty quickly, right? You can finish a question in maybe under 20 or 30 seconds. So number 12 is interesting because we have a product in the first portion of this expression, and then the end we have an added 5x to the 4th. Now this is a totally different situation than what we've been working on this entire page, right? So first focus on this and then see if it combines with 5x to the 4th. 2 times 3 is 6. X cubed with x is x to the 4th. Okay, so what's interesting here is 6x to the 4th plus 5x to the 4th. Well, now we literally have the same variable with the same degree. Okay, just give you a little bit of an explanation. If you have x squared and you try to add it with an x, you can't really combine these. These two have different degrees, and therefore they are not the same exact term. X squared is totally different than x. Okay. The only time where you're able to add the two terms together is if they have the same degree. So, like, this is literally x squared plus x. But what we've been doing this entire year is something like 5x plus 6x. Well, you see that they have the same degree, so that's why you can add them together. 5x plus 6x is 11x. Okay. Same thing with this. 6x to the fourth plus 5x to the fourth. They have the same degree. They have the same term of x, and therefore the final answer is going to be 11x to the fourth. Okay. Which value is greater, x times x to the fourth or x to the fifth power? Well, I hope you realize that they are indeed the same. Okay. Let's move on. Okay, so now we are diving into the world of dividing uh, with like bases with exponents, right? So, got to be careful here. This is a little bit different, and you can already kind of assume what we need to do, right? If we multiply similar variables with together, we add the exponents. Well, guess what you're going to have to do when you divide like bases, right? So I'm going to go ahead and rewrite 3 to the 6th as 3 times 3 times 3 times 3 times 3 times 3. 3 squared is 3 times 3. Now, remember back in elementary school when we had to learn about how to simplify something, right? If I have 6 threes in my numerator and 2 threes in the denominator, technically, wouldn't I be able to cancel a 3 on top and a 3 on bottom? Right? I do it again and I realize, oh, how many threes do I really have left over and what side is it on? Right? We have 4 leftover threes in the numerator, and we end up realizing that that's the final expression. That's what's left over. Okay. Now, take a look at our original question. 3 to the 6th divided by 3 squared. Guess what my final answer is? Guess what the quotient of that is, right? It's 3 to the 4th power. So B works. 1 to the 4th would be a terrible choice. Like 1 to the 4th is literally 1. 81, is that correct? Well, let's just double check. 3 times 3 times 3 times 3 is going to give me that 9 times 9, which, yes, it does work. 81 is also correct. Okay, so let's create a rule for this. I hope you realize it's just the same as multiplying, but it's instead of adding the exponents, we subtract, right? So to divide exponents with the same base, subtract the exponents and keep the base the same. We call this the quotient of powers. Okay, the quotient of powers. And it's really when you divide x to the a divided by x to the b, you end up getting x to the a minus b. And if a is less than b, then x to the a divided by x to the b is going to be, 1 over x to the b minus a. So I'll go ahead and explain this one with more detail, right? So you can see, class, that in number 14, we were given a situation where 3 to the 6th and 3 to the second power, and the 3 to the 6th was in the numerator, and 3 to the second power was in the denominator, right? So we just subtracted, we end up getting 3 to the 4th. No problem, right? So my question, though, and maybe that's the next page, I always do this, is what would happen if you ended up with like something like 3 to the 4th divided by 3 to the 7th, right? You could see here, class, that 3 to the 4th is just 3 times 3 times 3 times 3. And then 3 to the 7th, obviously, is 7 of those, right? So for me, I like to describe this as kind of like a competition between the numerator and the denominator. If you ever are given this situation, you have to realize which side has more threes, right? The side that has more threes is the side that will have the remaining leftover, right? So 3 to the 4th battles 3 to the 7th, and they take each other out. Like one by one, they take each other out. And then you realize, oh, there's 3 threes in the denominator, right? So you could see that, even though 3 to the 4th divided by 3 to the 7th, you technically would have gotten, running out of space, but you would have gotten 3 to the negative 3. What does that tell you about negative exponents, right? You can't leave an exponent as a negative, and instead 3 to the negative 3 is kind of like saying the numerator lost by 3. If the numerator lost by 3, your final answer should be 1 over 3 to the third power, which means the denominator is the winner in this case, right? And then obviously you actually can't leave your answer like this, because if you know what 3 to the third power is, you have to solve for it. So that's going to give me 1 over 27. Okay, I think that's another lesson in this module. So don't worry if that was a little rushed for describing negative exponents, but that's basically what you do if your numerator has less terms than your denominator. Okay. All right. So I'm looking at the next page, and I'm actually going to stop the video. I think this is a perfect time for you to try these problems on your own. And yeah, let's discuss in class in person. Thanks for watching.